Okay, so if you are if you don't have any class ongoing right now, we can start. And for the sake of the when I say for the sake of being coherent with other classes, I could propose to have our class doing on Thursday at 10:30, when is the normal time which is published, so that in case you plan to do the courses of Tuesdays on Tuesday, we can go with that. I hope that these first 2 weeks were time for adjustment. To me, having a 1 day before notice regarding the time of the class, I thought it was okay. And always, if I had any negative comment from you, I would always consider that. That's why we had this class. But from next week on, I propose to have this class on Thursday at 10:30. Always your concerns, you can email them to me, okay? So for now, we can start. So regarding the class, so today we are going to cover the solution of linear systems. So that's what we are going to start with first. And okay, let me see if we have a couple of comments from you. We do. No, I think we might just have it on Thursday for now. Okay. So the material, yes, Joyce, you're right. So far we have had we had the classes. It has been like 2 times. This would be probably the 3rd time that we are having the classes on Tuesday. From now on, we can switch to have the regular one fixed on Thursday. Okay, Joyce. So for the moment, we'll have class only on Thursday. Then extra material, which I can record and put them on YouTube, or I can share the videos with you. You can follow up the seminar sections with the solutions that I provide, where I record myself, where you are not at least live. Okay. So let's move on. And
Professor Falim.
yes.
Para se të nisim pyetjet, falim mësimin, a mund të bëj një pyetje?
Patjetër.
A është e mundur na çoni një kopje të zgjidhjeve të detyrave të shtëpisë? Sepse I kemi dorëzuar detyrat, po unë personalisht nuk jam plotësisht e bindur për zgjidhjet që kam dhënë.
Patjetër, po. Jo, patjetër që do japim zgjidhjet. Ndërkohë për ushtrimet e shtëpisë, nëse leksionet faleminderit për komentin dhe për pyetjen. Dhe ndërkohë do thoja për nga java e kaluar, shikojeni pak me kujdes gjithë ushtrimet që kemi pas të slajdet. Dhe disa ushtrime të zgjidhura, ato lecture notes që kam pasur unë, i pata bërë touch në slajdet. Detyrat patjetër do I zgjidhim dhe ato. Një koment mund të bëj këtu te çështja e detyrave. Okay, Joyce, yes, we can. Regarding përse përket materialeve, thoni keni çështje midis LMS-s dhe Google Classroom? Po. Shikoni, normalisht për mua është shumë e lehtë të vendos gjithçka në Google Classroom, është goxha e lehtë, por disa studentë më kanë çuar email thonë profesor, nuk aksesoj këtë ose atë, nuk e ti kalojmë gjithë në Google Classroom, dakor, në rregull. Duke menduar që LMS-n e keni goxha më të lehtë, mendova që një pjesë materialeve mund ta mbajmë dhe andej, por për mua është në rregull. LMS-ja ka një mekanizëm pak më automatik përse përket menaxhimit të detyrave, por dhe Google se ka dhe keq. Okay, we go on. Shumë mirë. Okay, we go like that. Any other comment or question? Okay, so let's move on. And today we are going to go over the solving of solving systems of linear equations. And so far we have covered error calculation, where the major approach that we used, it was Taylor series expansion, and also, of course, not only that, but we also talked about how we can calculate the approximate error and the true error. So we had these 2 values. We went over root finding, and in root finding, we discussed the Newton-Raphson second method And at this stage, I could suggest, if you have not done it yet, to go over the slides of last week again in detail. I hope by now you have submitted your homework, and the solution of the homework, of course, I'm going to provide it to you so you can see the complete solutions. And in the last week's notes, there was also you have some a couple of examples regarding the optimization chapter, which is mainly minimization of specific functions. That was the approach that we used. So please go over this optimization chapter, which is covered in the textbook. Now, we're going to go over linear algebraic equation. So in order to discuss on this topic, we need the matrix notation. And the matrix notation, I'm pretty sure that you did a good job in linear algebra when you took this course in the first year, and you did solve systems of linear equations then. And for this, we can use the Gaussian elimination, or GE, as is mentioned here. The Gaussian elimination can be also formulated in different forms, where one of them can be the LU factorization or LU decomposition. We'll mention what these are, and we can also have the iterative solution techniques. One of the iterative solution techniques can be the Gauss-Seidel. Now, when we say that when we have matrix notation is needed, mainly we need the linear algebra principles, especially when we have coupled quantities. So if we have coupled quantities, for the moment, I don't know how much of the board you can see, but if we have three different variables, y1, y2, and y3, if all of these three variables, they are coupled with respect to each other, the best thing that can be done is to use the linear algebra principles, because y1, it can be equal to 3y2 minus 2y3. This can be equal to y1 plus y3, and y3 can be 3y1 minus 2y2. So if we have a look at this system that is written on the board, this is a coupled system. It's a little tricky, it might be difficult, but we can always try to solve this one. Of course, this is relatively simple. We can also have some constants, or here we could also have derivatives of these functions. So y1 can be a function of the first derivative of y2 and so on. And now, if we have such a system, first thing that we can try to, we can make this better looking. So we can rewrite this one. So this can be written as, we can immediately write this one like this. We have 1, minus 3, 2. Then we have here minus 1, 1, minus 1. And here we get minus 3, 2, 1. If we multiply this one with y1, y2, and y3, this is all going to be equal to this expression. So we did not do a very complex task for the moment. We just had all the terms on one side of the equation, and we extract the coefficient as they are shown here. And in this system, this is called the coefficient matrix. So this is the coefficient matrix A. So we denote this one with a double-headed arrow. We multiply this one with an unknown vector y, and this is equal to 0. So if we solve this this system, which means that we have to figure out what is y1, y2, and y3, which in this case will be constant values, but it will depend, of course, on the nature of the matrix A. If you remember the terminology that we have used in linear algebra, this would be like determining the null space of A. Since this one is equal to 0, this is like a null space. So this example, which is shown here on the slide, what we see, apparently we see that we have the equation of motion of a certain system. The equation of motion, I'm pretty sure that you have seen this one in the first year. The equation of motion is always written like this. Force is equal to mass times acceleration. Okay? This is the equation of motion. And you also can see from the slide that the second derivative of x, which is measured in meters, that would be the acceleration. And this acceleration would be equal to some force terms which are written on the other side of the equation that are seen here. But in systems that are interacting with each other, we can have, for example, it looks like in this slide we have three masses, mass M1 and M2 and M3. Their motions are coupled together, and that's how, and solving for x1, x2, and x3, that means to distinguish or to figure out how they are also related with respect to each other. Let's move a little fast. So before we cover these topics, it's needed to have a review of linear algebra. So this matrix A that we've written, we can denote this one, the matrix A, this is denoted as Aij. That's a matrix. So any element which is Ij, where I can change is the number of rows, J is the number of columns, times Y. So A, this is how we can show here. An example, it's this A which is 512, 137, 278. And if we have a look at this matrix A, that's also a symmetric matrix. Then I want to remind you, or we can go over a couple of examples. So, and in order to be fast, I could also suggest to you to use this Octave Online, where it's also, it does not, it's very flexible. So let's assume for a moment, let's see what we have here in this slide. We have this, let's assume, and I guess you already got all the slides with you. So let's see what we get here. So A, it's just a matrix, okay? So here we have 1, 4, minus 9, 7. Here we can, this is a 2 by 2 matrix, and we can write P is equal to poly of...
question mark.
Okay, this is dictating for me, sorry. So what we see here, we have the matrix A is 2 by 2. With this code here, P is equal to poly A, what this finds the characteristic equation. And the characteristic equation is the equation whose solution are the eigenvalues. So it looks like here, in this case, the P values that we just got here, they are given right here. Sorry. No, it could not do it. It's 1 minus 8, 43. So the coefficients of this polynomial, it's 1, minus 8, and 43, which means that we are talking about a polynomial which is x squared minus 8x plus 43. Okay, that's the second order polynomial. That means we have two roots. Now the roots, we can write this one, r is equal to roots of
Question
p.
mark.
It looks like this polynomial, it has two solutions. One is 4 plus 5i, it's a complex number, and they are complex conjugates of each other, it looks like. And it's 4 minus 5i. In question 5 of the homework that you have already submitted, you had a polynomial where the roots were complex numbers. And now there was a little tricky question, where the solution, it could be provided as if it's a vector, because these complex numbers that you see also here, they can be interpreted like vectors. So we can have a matrix, we can get the characteristic polynomial just by writing here poly A, we can get the roots, and these are the eigenvalues of this system. And we can also find the eigenvalues like this. So we can say just, of course, you do remember probably these.
Question mark.
So these are just A, this finds the eigenvalues of A. At the same time, we can...
Question mark.
Question mark. I don't know how, I need to turn off this dictation thing, but... no, let it be for a moment. Sorry for interfering like that. Vd, this is equal to Ig. So these are the eigenvalues and the eigenvectors. And I hope that for the sake of a much deeper understanding, that you do remember that the eigenvectors of a certain matrix, they can be used to construct another matrix which diagonalizes the matrix A. So, so just, I hope you can, Wait a second. I just want to see what part of the board you are following. So here we are. I guess we are presenting. So just for a moment, I just want to shift to switch to the use of the board. So we have a matrix A, and from this matrix A, we can find the eigenvectors, which can be V1 and V2. And this V1 and V2, they can compose another matrix, which is 2 by 2. If we multiply this one with a diagonal matrix, which is lambda 1, lambda 2, we multiply, so I think we have that the V inverse times D times V, we get a relation which is equal to the A. Now, I want to remind you also about the SVD. SVD is the singular value decomposition of any matrix A. So this is going to be equal to USV. This is going to be the singular value decomposition, which means that if we have any matrix A, if we multiply this one with a vector x, we know what happens. This vector x will be rotated and its magnitude can be compressed or extended, or it can become longer. So this is going to be, so let's call this one A times x0. This is going to be x final, okay? Now, at the same time, we can, this A is equal to U S V transpose times A, sorry, A is gone, because the multiplication of these three matrices, this is going to be equal to A. This is just a very short, I don't want to stay too long with this one, but what happens is, with the singular value decomposition, is that this vector x0, which, if we had just the A, we would have the immediate rotation. We can write this one. This can be represented as, let me try to do my best for a moment. So let's assume in two-dimensional, in 2D, if we have a vector that goes like this, if we multiply with A, we immediately get some result. But now, we can also write this one. First, we can apply this operator V transpose on x0. This V transpose, this is just a rotation matrix, okay? Which means that this, keeping the same length, this can become something like this, okay? So this was the x0. This is now x1. And so we are done with this one, and what is left is that we have U S times x1, okay? So this was the rotation matrix. This matrix S, what it does is that these components here, it multiplies with two sigmas, which are the singular values. And this S, to remind you, this is a diagonal matrix, which can be written, so let's assume this is again a rotation matrix U, and this S, this has a sigma 1, 0, 0, sigma 2. Okay, and this is going to multiply this x1 vector. And so if what these sigmas do, they're just going to change the magnitude of this vector. So maybe this is a little smaller, this gets a little longer. So this vector x0, x1, finally, we can get, let me try to find a blue pen. So out of here, we can get, no, doesn't work, I'm not lucky enough. So we get this x2 here, okay? Now, I'm trying to do my best in terms of trying to make it clear that from x0 to x1, the length of the vector or the magnitude is not changing, okay? Because it's simply a rotation. Then we multiply with the sigmas, which multiply the base vectors. So the projection of the red vector, they were here. Now we get this x2. Then finally, this x2, we have this operator u, which is another rotation. It multiplies this x2. And with the objective of keeping the magnitude the same, let's assume that we get this x3 for the final result. You know, the blue is So we get, let me do this in a red, and we observe that initial x 0, we just rotate it, then we multiply the major axis with two coefficients sigma 1 and sigma 2, and then from x1 we get x2, then we have the final rotation. So it is good to think in terms of all these matrices, what the matrix does. In principle, it can be decomposed in a very nice way, in a very beautiful way, which can provide to anyone a lot of insight on specific systems. So when I say specific systems, I can give at least 3-4 different examples where there are specific vectors that have certain properties in number theory, for example, and whenever you apply a matrix, it's good to represent these properties as with the principle that you have learned when you were in linear algebra. I'll go back to sharing the screen. So, and here, let's see this matrix A that we had. Let's have a look what A is this one, and let's see if we can. We have here USV. This is equal to SVD of A. Here we are. We get these three matrices where you have U, S, and V. U and V, they are pure rotation. S is the sigma, which I was trying to show. Is we have only two components over there. And if we multiply here U times S times V transpose, we get this. So this is what we should get. Okay. So enough with this short overview, but which I find it very essential, very important, especially the eigenvalues and the SVDs. Let's move on to the other materials. So here we have, when we talk about matrices, we have some terminologies which are used, where one of them is the banded matrices. The banded matrices, it's an equivalent term similar to the bandwidth of a certain signal or bandwidth of a certain frequency. Here we have a band of 3. This matrix A, which is these two on the bottom, the one on the left, it's an upper triangular matrix. The lower part is all zeros. The one on the corner, it's a lower triangular matrix. Let's see what we have. We can also define permutation matrices. A permutation matrix, they are as the one which is shown here. So if you see this P matrix, what makes it different from an identity matrix is just that it has exchanged row 1 with row 3. So if we multiply with this permutation matrix, this matrix, what we are going to get, we'll interchange the first row with the third row. So this is how it goes. And now let's move on. Regarding the linear systems, we have, whenever we have... Sorry, I have a question?
Po, profesor, më fal që ju ndërpres, por unë ju informova se fola me pjesën tjetër të klasës që ram dakord për të vazhduar të njëjtën, po ju keni filluar, kështu që se neve akoma s'kemi mbaruar me profesor Betimin.
Po, ju lutem, unë fakt do kërkoja një sqarim të sepse shumë nga shokët më komunikuan që nuk kanë leksiona apo e keni lëndën e grupe.
Po, me sa di unë, ne e kemi të plot. Nuk e di tamam, domethënë, po me çmora vesh nuk po e bëjmë gjithë, po ne jemi gati rreth 50 veta, 40 sa veta, 50 veta.
Shiko, çdo gjë zgjidhet. Kjo gjë që po this class is being recorded, so no one is going to lose it. Por, unë kur futa në leksion, më komunikuan që mund të vazhdojmë se s'kemi mësim tjetër. Prandaj u isha pak në
Profesor, më falni, mbas sekondën kish kuptim sepse grupi tonë nuk i ka ardhur asnjëri linku që kishim mësim me profesor Betimin. Në fakt ne ishim gati që në mëngjes, por që do ta marrim vesh kur të kemi mësim.
Kështu që thjesht shiko, çfarëdo që ndodh, we'll try always to adjust to the best of of what we can do. But so at this moment, is anyone having another class at this moment?
Yes.
Ka?
Po janë goxha që janë me profesor Betimin tani duke bërë mësim.
Pra po vetëm grupi A është, se grupi B është gjithë këto.
Okay, probably that's the
Se
case.
për grupin B.
Good. So apparently it's a group separation class. That's fine. Okay, so whoever the other group that is having the class with Professor Betim, we can go over this recorded material for sure. But as I said, I was just yeah. Now I understand this a little bit better. What is going on? Okay, let's continue with our session here. Okay, and until Thursday, at least I'll put some more material for you to follow on the chapters that we are ongoing. But then, since it is past 12, is the class getting close to an end, or? Seksioni grupi tjetër apo vazhdon mësimi apo?
Po, ne jemi duke vazhduar mësimin akoma me profesor Betimin.
Dakor, vazhdoni, mos e prishni mësimin, vazhdoni.
Tani vetëm një diçka, nëse e krijoni dot mundësinë ose kushtet që ta zhvillojnë të njëjtin po në të njëjtin orar që përcaktuat juve në 1:30?
Do e bëjmë atë, pa më mirë.
Okej, dakor, faleminderit. Kalofshi mirë.
Yes, we can. Denado, we can upload this on YouTube. Yes, and whatever we put on the we either share the video on Google Drive using the institutional emails, but for other reasons we can also publish this on unlisted videos on YouTube, so no one can track it down. But yeah. So it looks like we are having an effective class with one group of the class. Okay, so let's see now regarding the solution of a system, and let's assume that we have an equation of two unknowns where we have x1 and x2, and we have three possible combinations. One of them is when actually all of these are problematic. We have the first case, we have no solution. The second case, which in the middle of the slide, we have an infinite number of solutions. And the third case is that we have an ill-conditioned problem. With ill-conditioned, what we mean is that with minimal changes in the input of the system, we get large errors in the output. Okay? So all of these, they are not the best situation to deal with, and you can easily see what this is the depiction as a graph. So the first one, it has determinant equal to 0. The second one, also determinant is 0. The third one, the determinant is some epsilon, something much smaller than 0. Now, the approach that we can use to solve a system is to reduce the system to an upper triangular system or lower triangular. But for the moment, let's have a look at the system that we have here. So the objective is to solve whenever we have AX is equal to B, the objective is to transform the system such that we get here UX is equal to C. Okay? So this is an upper triangular matrix, and we start from the normal matrix. So it looks like we change the B, and we need to, and the X is the same. So the idea is to use back substitution as it is shown here to get the X1, X2, and the X3. Let's see what we have here. We'll see how we use this back substitution, but if the system of equation, if the variables are not too many, because we can have systems where we have 7 unknowns, that would mean that for 7 unknowns, so let's say that when xi, which is an unknown, where I is from 1 to 7, then that means that the coefficient matrix A would be also another 7 by 7. Okay? And using the graphical method to solve such a system, it would be very difficult because we cannot visualize effectively the 7-dimensional space. But for any problem which has two unknowns or 3 unknowns, it's relatively easier to see where 2 curves or 2 planes or 3 planes intersect to find a single solution. Now, that's a little difficult, but another one which is very straightforward is to use the Cramer's rule. The Cramer's rule, it's made possible by, if we have the system which is shown here on the slide, AX is equal to B, we can find each respective value of X by substituting the respective column with the answer vector, with a B. So this would be the Cramer's rule. Now, let's see. I think we are going over, this is how the Gaussian elimination will work. The code, I mean, if we write an algorithm in order to solve this one, this is how it is going to look like. And the general idea is that if we have any, let me try to get a realistic example. So the idea is to make this upper triangular matrix, we want to zero these terms, okay? And the expression, we're going to write it like this. R2 star, for example, in order to make this zero, we are going, sorry, remind me when I forget to, I want to stop presenting, and I guess now you do see the board, right? So, this R2 star will always be written as the first R2 minus lambda times R1, okay? So this is how we are going to try to make this zero. And in order to make this zero, the lambda in this case is going to be 2/4, okay? So here we get R2 minus A21 over A11 times R1, okay? So in this case, A21 over A11 is 2/4, which means that this is equal to R2 minus 0.5 R1. Okay, and let's see. If this is 2 minus half of the first one, we get 2 minus 2, we get the 0. So we can successfully make here a 0. Then, in order to make this 0, we need to write that R3 star, or the new value of R3, is going to be equal to R3 minus lambda. Maybe it is best to consider this one lambda 1,3. We call this one lambda 1,3 because we're going to couple R3 with R1 times R1. And as we said, this lambda 3,1, this is going to be equal to R3 minus, this is A31 over A11 R1. So A31 over A11, it's 8/4. Okay, so we get the 2. So this is equal to R3 minus 2 R1. And if we check, we are going to have here R3, this is 8, minus twice the 4. 8 minus 8, we get the 0. So we can successfully obtain a 0 here. Okay? So this is the steps that one has to follow to produce the upper triangular matrix. So again, I'm just going to write here, Rj star is always equal to Rj minus lambda Ri, okay? And J is always larger than I, which means that to get an upper triangular matrix, we're going to zero out the later terms using a row which appears above, okay? So in this case, what was essential, if we have a matrix which is 3 by 3, what we need to figure out these terms. Lambda 2, 1. Lambda 2, 1 is used to make this 0 use the first row. Lambda 3, 1, which here, I hope this is clear. This is minus 2. And then we have also the lambda 3, 2, which is going to make 0 this third element. okay? Yes, so we are going to have three different numbers in this case. So this is the how we can obtain the upper triangular matrices. Now let's see if we have anything. Let me try to share the screen back. Okay, so I think you do have already the slides. So what can be useful is the following. We have a couple of examples. We have A and B, and always the objective is to find the X. So this is A. This is the matrix A.
Question mark.
This is how it looks like. And the B here, this is the B. And the solution, actually, this can be as simple as this.
Question mark.
Apparently, the B, the solution is something like 0.1. Let's see. And I guess here in the slide here, so in the algorithm that we write, when we were using the board, we said that we have this lambda 1, 2 or lambda 3, 1. We were dividing the terms that we want to make 0, okay, with the term that is used as a pivot. But we could run the risk of whenever we're doing these divisions. Let me bring it back just for a moment. So the risk that we may run is the following. We are presenting, stop presenting. Let's go back to here for a moment. So I hope you are seeing this. So whenever we find these numbers were like this. But you can see that in here and in here, we divide it with A11. It could be some cases where this is called a pivot element, okay? If this is 0, we may run the risk of dividing by 0, which makes us to get some non-numbered terms, okay, because the division by 0 is not defined. So what can be risky is where the pivot terms, for example, if AII is 0, or if AII is a very small number, some epsilon, okay, let me add this epsilon. This creates a lot of error whenever we try to solve the system. So, and for this one, the code that we showed here, now screen. So the little piece of code which is on the slides, it can become problematic if we don't take care of fixing the issue of the pivots. Okay. So with this with this matrix A, which is shown, if we try, let's see, we try to find the solution as follows. We have the A, we have the B, and apparently the solution for this A and B, it's 2 minus 2, 3. So the solution is going to be, 2 minus 2, 3. This is the solution for this specific case. Now, if we have this other A, if you just double check, in this, if we look at this A, we see that the first element is 10 to the power minus 4. 10 to the power minus 4, which is some epsilon. It's a very small number, which means that we can run the risk of having errors when we try to solve this one. So, and for the moment, we're trying to get the solution X using the code which was shown, which was shown also in the PowerPoint, and this is called naive Gaussian because it does not consider when the pivot elements are zeros. Now, this was 10 to the power minus 4. We still got a solution. Okay, we got a solution here, but let's have the same system. And let's assume that the A11, it's not a negligible number, but it's purely 0. Okay, so that's what we have. The B, we don't change it. And let's try to solve this one. Apparently, we cannot find the solution. But we can be a little more careful when we write the code for this one, which and what, for example, the A is this one. What we can do is that instead of using this A, we can multiply this A with a permutation matrix. So
Question
I2,
mark. Question mark.
sorry, this is not the
Question mark.
I2, this is the identity matrix, okay? If we want to use a permutation matrix which changes the A, we can define a P,
Question mark.
which is here 0, 1, 1, 0. So let's have a look at this P. If you multiply
Question
this
mark.
P with
Question
A,
mark.
so we might get this matrix A rather than the other one. Now, if we have the A as is written right here, that means that the pivot elements are not 0. So in our code, we will not experience any division by 0. So if you want, then the A, it stands as it was. If we try to solve this one using naive Gaussian, we get no solution. But if we use the Gaussian with pivoting, we just change this n with p, we find the solution with just exercising a little more care, okay? Now, let's have a look at these other examples here. Let's assume that this is a matrix A.
Question mark.
So it's a 4 by 4 matrix. Then the B, this is the B. We have a 4 by 4 matrix. If we try to solve this one using the Gaussian elimination, actually, let's have this first. Let's see if naive Gaussian solve this one. It looks like we do have a solution, okay? So the matrix A, which is shown in this screen, multiplied by this X vector, we get the B vector. Now, let's assume, let's make a change of this matrix A by just making this element -2 to make this 0, which means that let's make this A, let's make this 0, which means that A
Question mark.
2, 2, let's set this 0, okay, as shown here. And let's see if we can, I guess you can see the changes that we did right there. So it looks like this system, it does not have a solution if we use a naive Gaussian. Now, we can, if you see no solution, the first thing that we can consider is to look at the determinant. Determinant is 0. You go back to the old information you have from linear algebra, you say, okay, if the determinant is 0, you have two possible two problems. The system can have no solution, or it can have an infinite number of solutions. Now let's see which one is in this case. So we could not solve this one using the naive Gaussian, okay? Probably this problem can be solved if we use if we can do pivoting. And as we said before, the pivoting is just we exert a little more care to cancel out the 0 pivots. Okay, this has no solution at all, apparently, even with pivoting. So this had unique solution. This had unique solution. This the first exercise. Here, no solution. We got no solution here. And then let's try to modify this matrix A again by changing the A to 4. So let's make this 4 here. Let's make this one also 0. So this element here that we observe that we want to make this 0, it's A to 4. So we have here A to 4. This is equal to 0. If we, this is how we can locate this one, A to 4, this is equal to 0. And let's try to solve this system again. So A, we can see how this looks like. And this looks like this has no solution either, okay? We can try to determine the determinant. It's still the same thing. But then let's spend a little time and let's see if this system really has a possible solution. So if we look at this, the last matrix, which is 4 minus 1, 2, 3. 4 minus 1, 2, 3. I guess you have, so you might immediately try to figure this one out. Let me see what the matrix would look like. It was 4 minus 1, 2, 3. And the other element is 0, 0, 7, 0. 0, 0, 6, 5. And then we have 0, 0, 0. This is x1, x2, x3, and x4. This is all equal to the b vector, and the b, it's equal to, let's have a look what b was. This was 20 minus 7. 20 minus 7, 4 and 6. So the back substitution, how it works, it's called back substitution because we need to find the x4 first. Okay, so in this case we have 3x4. This is equal to 6, which means that x4, it's easy for us to figure it out. We get a 2. Okay, then being back substitution, we go to the next one upper equation, which provides for us the 6 times x3 plus 5 times x4. This is equal to 4. But now this x4 is 2, because we found this one, so we get a 2 here. And 6x3 is equal to 4 minus 10. This is equal to minus 6. So we get 6x3 is equal to minus 6, which means that x3 is equal to minus 1. Okay, so we found two values. Then we go to the one upper system of equations, and we see here that we get 7 times x3. This is equal to minus 7, which means that x3 is again equal to minus 1. And this system, it looks like it's going to provide for us an infinite number of solutions. And regarding this, let's have a look at the final equation. We get here 4x1 minus x2, so minus x2 plus 2x3, but x3 is minus 1. So if you allow me, well, let's leave this in x3 plus 3 x4, this is equal to 20. Sorry for using a board like this, but then if we substitute these values, 2x3, we get 4x1 minus x2, 2x3 is minus 2, minus 2 plus 3x4, x4 was 2, plus 6, this is 20, and then it's, this is 4 minus 4, 4x1 minus x2, this is equal to 16. So we do have a solution, but it looks like we have an infinite number of solutions because we don't put any constraint on x1 or x2. So this matrix A, the determinant here, it is equal to 0. The determinant of A, this is 0. Then when the determinant of A is 0, what are the two options? One option, we have no solution. Okay. The other option is we have an infinite number of solutions. It looks like this A that we have here, we have this case. Okay, so we have an infinite number of solutions. So whenever we try to solve this, we may have to exert also a little more care. And then if you go back where we were, let's share the entire screen. I guess it might be easy for you to go over the slides. So these were the examples. The answers are here. So it looks like the last matrix, it has an infinite number of solutions. Now we can skip this part a little faster, which does the which counts the number of operations that are needed for the Gaussian elimination. So what we did so far, it was that we have a matrix A, we reduce it into an upper triangular matrix, and then solve that one. This example which is on the board, this is a back substitution example. Now, we have two major methods to solve the system of linear equations. One of them is direct. What we mean with direct is that we can count the complete number of steps which are needed to calculate something. Whereas the iterative method, it's a method where we can continuously try to improve the solution by tracking down or by monitoring the error which is in the system. Now, the direct method, we have these three. Actually, there are more, but maybe these are the most commonly well-known methods. So if we have AX is equal to B, we convert the system into UX is equal to C, where U stands for upper triangular. This is called Gaussian elimination. We have another decomposition, which is called the LU decomposition. And if you are a little careful, what I want to say is that the first two are equivalent. If we do all the steps in a well-structured way, this can be considered equivalent because on the path to finding U, you already find the L. Okay? Pra ku gjeni unë gjatë rrugës, po t'i bëjmë veprimin me kujdes, do shikoni që keni gjetur edhe L. So being careful about these, that's what we do. Then the last case, or the last what's the name? Method that we can talk about is the Gauss-Jordan elimination, where AX is equal to B is converted into IX is equal to C, where I is the identity matrix, which means that X is equal to C. Now, LU decomposition, this is how LU decomposition works. Now, I think, so what LU decomposition means is we write the A as A is equal to L times U. Pra gjejmë dy matrica, njëra është lower triangular, tjetra është upper triangular, dhe po t'i shumëtojmë të dyja del A-ja. Tani upper triangular matrices e pam sa e lehtë ishte që t'i zgjidhim. So we saw how relatively easy it was, okay? Now, we don't get just a triangular matrix, we get two. In order to do that, we do this. In the example we solved before, a few minutes before, you already saw these, right? So this, I wrote them on the board as lambdas, right? Like some coefficients. Now these lambdas, they are always equal to the number that we want to zero out divided by the pivot. So if we want to make the A21 and A31 zero, we divide these elements directly with the pivot. Pivot element is element of reference element. So using these steps, we get this, but then these lambdas that we wrote them on the board, they can be used to put immediately at the lower triangular matrix. So A is equal to L times U. In Octave or in MATLAB, you can write as LUP is equal to LU of A. You can directly get the lower triangular and upper triangular matrix. Now, here we have an example. And here we have the A. Apparently, it's a 3x3 matrix, and we want to find these. So you can go over. Let me have a look here. This is 4 minus 2, 1. Let me see if I can. And one thing that can be noted is that whenever I have a triangular matrix, the determinant. And by the way, can I have at least one of you say something? Is everything okay?
Yes, for sure.
Thanks. So, yes. Now, probably I could go back to you're presenting, stop presenting, so you can have a look here. So, one little note. Triangular matrices the determinant is always equal to the product of the diagonal terms. Okay, so this is equal to AII. When I, it goes from 1 to n, which means that this is equal to A11 times A22 times ANN. Okay, so this is how we find the determinant. Now in this case, let's have a look at an example. So here we have A is equal to 4 minus 2, 1. Minus 2, 4 minus 2, minus 2, 4 minus 2, 1 minus 2, 4. Now, if you look at this matrix, this is a symmetric matrix. It's a good-looking one. And we want to write this one, we want to decompose this one in this form, as a product of L times U. To do this one, let's try to obtain the U. To get the U, we want to make these zeros. So what is the first element we want to make zero? Is this minus 2. Then we say that lambda 2,1, this is equal to A21 divided by A11, which is equal to 2 over 4. Minus 2 over 4, which makes this minus 0.5. Okay? Then we have lambda 3,1 is a coefficient that can help to make this 0, which is going to be equal to the number we want to zero out divided by the pivot element. So this is the element that is going to be used to zero these, which in this case is 1 over 4, which is 0.25. Okay? So these are these elements. And then to do this, we see the following. We have R2 star is equal to R2 minus lambda. Lambda is minus 0.5. Okay? Minus 0.5. R1. Okay, then we have the R3 star, this is equal to R3 minus 0.25 times R1 again. And if we do these steps, finally, we figure out that, but let's save these. We need to keep these somewhere. And if you do all these operations, we can get all these, the U upper triangular matrix. And in the end, we can get that A is equal to 1, 0, 0. I'm trying to write down the L matrix here, okay? So this is lambda 2, 1, it's minus 0.5. Lambda 3, 1, 0.25. This is 1, 0. Then this lambda here, it's minus 0.5. If you follow the step, this is what you're going to get. Diçka që se kam thënë deri tani është kjo që kur bëjmë LU decomposition, ky lloj dekompozimi I veçantë është që këtë lën I mban diagonalet njësh. So you keep the diagonal terms equal to 1, and these three, the rest of the three elements, they are these lambdas that we generate like this. Right. So this is the L, and the U matrix is going to be 4 minus 2, 1. The first row, it does not change. The second row, since this is an upper triangular matrix, this is the lower part we know that are already zeros. This is 3 minus 1.5, and the last element is 3. Okay, so this is the L matrix, this is the U. And there is a property that if A is equal to the product of two matrices, the determinant of A is equal to the determinant of B times C. So we can see here the determinant of A is equal to the determinant of L times the determinant of U. So what is the determinant of L? Sa ka determinantin loja? So the determinant of L is a product of the diagonal terms, okay? So what is the product of the diagonal terms of L? It's 1, and this is also equal to we take the product of the diagonal terms of U, which is 4 times 3, 12 times 36. So it looks like the determinant of A is 36. Now, can I get any question from you, if you have any? Okay. So if you don't have any question, and since we cover, yes,
Unë jam nga grupi tjetër edhe u futa tani në leksion se po bënim me profesor betimin. Mund bëj një pyetje për detyrat e shtëpisë që nuk ka lidhje me mësimin që po shpjegohet?
jo, detyrat e shtëpisë nuk kanë lidhje me këtë materialin e ri, jo.
E kuptoj, po mund bëj një pyetje për detyrat e
Patjetër,
shtëpisë.
patjetër, më thuaj, po.
Te ushtrimi i fundit që kishim nga slajdet,
Po.
aty besoj të përdoret Newton method apo jo?
Po, ashtu ishte specifikuar drejt. Po.
Nëse përdorim Newton method në intervalin nga 0 në 6, derivati bëhet 2 herë 0, edhe bëhet del pjesëtimi me 0 2 herë brenda lupit, kështu që del error.
Dilte, po mirë, a mund ta shikosh ndonjëherë, edhe unë ta shikoj. Normalisht në zgjidhjen për 2-3 raste të veçanta e zgjidhem besoj për atë lloj ushtrimi.
Nëse do e marrim do bëjmë 6 iterime me hape nga 0.1,
Po.
atëherë 2 herë brenda intervalit 0.6 derivati bëhet 0.
Ta shikojmë ndonjëherë ose më dërgoj me email, ndoshta ta komunikojmë
Okej,
me
okej.
detaje, në rregull.
Okej, do dërgoj një email.
Bëjmë pyetje tjetër për këtë pjesën e sotme të leksionit.
Për këtë se kam ndjekur, kështu që besoj
Dakor,
në tjerë.
në rregull. Por materialet që janë të materialet e sotshme të PowerPoint unë i kam dërguar tek ju. Shpresoj që ti shikoni. Për çdo gjë tjetër, shiko, këto 2 javë të para ishin edhe një lloj u mësuan dhe pak we just got adjusted to the system. Javën që vjen do, siç e përmenda fakt në fillim të leksionit, do përdorim ditën e njëjtë. Unë atëherë për tani po e mbyllim leksionin. Për çdo pyetje shqetësim tjetër që mund të keni pas këtij momenti mund të komunikojmë me email. Atë mirupafshim.